Alright, so now let's start to begin into the very long discussion of Michaelis-Menten enzyme kinetics. So there's some certain assumptions that we make when we talk about these things. Those being that these are linear reactions. A single substrate gets converted to a single product. We assume that this is at a steady state where the enzyme substrate complex is equal to, the formation of that is equal to the breakdown of that. But again, this is supplemental material. This is not a substitution for a course. There's a hyperbolic graph that we use. This is used to basically just like we did with general chemistry when we talked about chemical kinetics. This right here is just a way of representing the conversion of reactants to products over time, right? So that's all that this is. Don't let people overthink this. This is sometimes called the Michaelis-Menten model, but let's go ahead and just divulge and show the equation for this. So the equation for this is where the velocity, or you could think of, I mean, if you're like me and you haven't taken a whole lot of math yet and you start seeing velocity, I prefer to think of this as the same thing as rate. You could say the same thing saying that the reaction rate, all right, the change in concentration over time, right? In this context, though, it's equal to a thing known as Vmax, which we'll explain what that is later, times the substrate concentration, times the concentration of our reactants, divided by something known as the Km, a Michaelis constant, plus the concentration of S. So this is the equation that we use to give us our hyperbolic graph. So I'm going to go ahead and just try my very hardest to draw this out on a pen. Some very fortunate people have software that enables them to do straight lines and things like that, and you can even draw graphs, like insert graphs into them. I can't do that. Anyways, so here we see substrate concentration versus velocity. And the reason why we do this is because what you're about to find out about some special features of Vmax and Km. So I'm just going to go ahead and graph my overall changes that's happening. As we increase the substrate concentration, how does this affect the velocity of it? Okay, so this is the general trend that it goes through here. And hopefully, I know it's not the greatest of examples. I don't know why I kept going on with this. But anyways, if you think back that everything really does come down to general chemistry concepts. That's what I tell anybody who's taking Gen Chem, because they're like, this is so abstract and so pointless. Yeah, you're going to use this a lot for the rest of your life, no matter what your major is, chemistry or biology or even geology. These are universal concepts. So let's look at what this reaction graph means. We have some points that we need to define real quick, though. The first thing that I'm going to define is the point known as Vmax. And Vmax would exist in a hypothetical situation right above this. This is Vmax. So if you remember back to general biology with Dr. Dini's class, when an enzyme is saturated, it cannot increase the reaction rate by increasing the substrate concentration, right? That's what Vmax is. It's a theoretical point, right? We can never actually reach Vmax. It does not. We've never seen this. And I'll explain why in a second, why Vmax is impossible to reach. Another point that we can make here, and I'll explain what this means again, if we were to go through here where we have half of Vmax, half Vmax there, or Vmax over 2 if you were to think about it. That's what this point is. The point at which we have this, the substrate concentration, okay? So the substrate concentration at half of Vmax, or you just say Vmax over 2, gives us this thing known as Km, the Michaelis-Menten constant, okay? So before I define Vm and before I define Vmax in terms of the way that we explain them, their equations, let's take some more time to really look at this graph and really analyze it. So what this is telling us is that from the beginning point here, which I'm marking in yellow, all the way up to until you reach Vmax, and I'm just going to say here is the arbitrary point to which I'm cutting off and saying this, but even from here to here, that's a little bit more obscure. From here to here, up until we reach Vmax, the rate limiting step is the actual delivery of substrate. So your rate limiting step up until you reach Vmax is delivery of the substrate, okay? Once you're at Vmax, okay? Once you're at Vmax, and I'll just go ahead and define this right here. I know we're getting crowded, but At Vmax, the rate limiting step is literally the catalysis, okay? The actual reaction that is catalyzing it, meaning once you have that concentration that's so high, the rate limiting step is the rate at which the enzyme catalyzes these reactions. To give you a reference point just of how insane that is, okay? So the enzyme known as carbonic anhydrase catalyzes 600,000 molecules of substrate per second, okay? Some of which can even be faster than that. This is literally faster than the fastest types of machine guns we've ever been able to create. This is a theoretical value. You will never be able to reach saturation where there's so much substrate that the Vmax, the rate limiting step, is dependent upon catalysis. I feel like I've stressed that enough though. So the way that we define these other two terms here, such as Vmax, well, Vmax is basically the reaction velocity at saturation. So this is at saturation. How do we define Vmax, in case you're curious? Well, Vmax is dependent upon what? It's dependent upon the rate of catalysis, right? So if I have a saturated enzyme and it doesn't matter how much substrate I add, it's not going to go anywhere. It's a first order or zero order reaction, sorry. So it's dependent upon the rate of catalysis, which we represent this as K2. Some people call it Kcat. I like to call it Kcat because I feel like that's more beneficial, but I'll explain why I'm using K2 here in a second. This is K2 multiplied by something known as the enzyme total. So the way that we can change the value. So Vmax, you can change that. It's not an indelible thing, right? You can increase the amount of enzyme that's present, right? Obviously to a certain extent, but you can increase more. I can pour more of my enzyme into this, and that's going to increase my enzyme concentration, which makes all of these two initial points here are not really valued. So I guess I should have said this earlier, that we had, assuming that that's what the steady state meant, we had a constant amount of enzyme. But if we increase the amount of enzyme, we can increase the reaction, right? But K2, the rate of catalysis, that is an intrinsic property of the reaction. That's as fast as it's going to go. You can't make that any faster than that because that's just how chemistry is, right? So this is how we define Vmax, right, as that. Now let's talk about what Km means and what this. So we know what Km is on this graph, right? It's the substrate concentration of halfway between Vmax. So this right here, this is the concentration that we reaches as Km. But the way that we represent Km mathematically, the way that we use our equations for this, is something known as K minus 1 plus K2, you can think of it as Kcat, divided by K1. So what the hell does this thing mean? Well, what I mean by using this is that when we're talking about the hyperbolic graph or the hyperbolic equation, there's some generalized overview of the way that we would represent this would be the enzyme reacting with the substrate in equilibrium to give us the enzyme substrate complex. This enzyme substrate complex is then going to undergo another reaction to give us a product and the free enzyme, which brings us right back over here, right? Now I've drawn this other arrow as very small because it's virtually astronomically small and doesn't really do much, right? I've never heard of a hydrolytic enzyme undergoing dehydration synthesis. That's just batshit crazy. That's why we don't even really bother concerning it. So the only thing that we have to worry about are really just three constants for this. The first constant is K1. Okay, that's the rate of formation of the ES complex. That's what it's associated with. And then the next one is K2. This is the catalytic rate, which we've already talked about over here. And then for the reverse reaction, this is K minus 1, because we're taking the inverse of the forward reaction to give us the reverse reaction, right? So what this means here, and the way that we define Km is the amount of substrate that we need to be able to reach saturation. That's what Km can tell us, right? Because if we have to have a lot of substrate to reach saturation, then that means that it's not binding very well. It doesn't have a strong affinity, which I've made a video explaining what affinity is, and actually I think it was for another course, but it still applies to this. So Km can give us details about the relationships between the substrate concentration and the speed of the reaction itself, right? So that's what Km defines. I'm going to go ahead and just explain here that Km has an inverse relationship with affinity. And that makes sense, right? If we have to have a lot of substrate to add to reach Vmax, because if we have to have a lot of substrate to reach halfway between Vmax, we have to have a lot to reach Vmax anyways. That means that the binding sites, the affinity, the eagerness for this enzyme to form the ES complex is not going to be very large. So this is what this represents in terms of graphically here, if I just kind of reiterate what I'm talking about here. But also, if we were to look at this, well, what do these associated values mean? So what I mean by that is an equation is worth 1,000 words. If I look at this and I say, okay, if I increase the value of K2, the top number, that is going to increase my Km. That means that the concentration of substrate that it takes me to reach half of Vmax is going to be really, really high. And remember that K2 is what? The catalytic rate, right? Also, by the same notion, if K1 is a very, very large number, okay, because the enzymes and substrate come together very easily, then that means that Km is going to be small, because as Km goes up, K1 goes down, or as K1 goes up, Km goes down, right? And so for K minus 1, I don't really take that into a whole lot of consideration, just because we're not really worried about that. I just got out of organic chemistry, and we don't really care about reverse reaction. We only care about the products we're interested in. But understanding the K2 and K1 for Km really helps us understand the relationships that we're expressing with this. So another thing that we could say about this whole equation here is that as the catalytic rate goes up, as catalysis rate goes up, then that means that the affinity, so as K2 goes up, that means that the affinity, the overall Km, will go down. And that is kind of crazy to me, that it's this balancing act here. So how do we measure the perfection of an enzyme? We'll talk about that later, but we have to consider both the Km, the affinity, and the K2, the efficiency of the reaction, the catalysis rate. So the next two terms that I really want to define, and they're not superbly, well, I mean, they're very important, obviously, but is ET, which I defined it up here, I just don't have room for it. This is known as enzyme total, and it's just that. You take the amount of E that you have from here, and you're going to add that with wherever you see an enzyme, right? So the ES complex would be considered a part of the enzyme total. And this plays a role in Vmax, right? Because Vmax is dependent upon what? The amount of enzyme you have, whether that be in the substrate that's bound there or that's free, where it doesn't matter, right? Because that's both contributes to the overall Vmax. What I wanted to say about this is, how do we measure the overall, how well something is, overall enzymatic efficiency? Well, to measure the overall enzyme efficiency, we need to take into consideration two things. One, the first reaction here, right? How well this enzyme is going to bind to its substrate, and that's the affinity part. And then the other thing that we need to take into consideration is the K2, right? The rate at which it's going to catalyze these reactions. And some of them it's like 600,000 molecules per second, and some it's like 2 molecules per second. So obviously there's a big difference between those two things here. So the overall enzyme efficiency, the way that we represent this is as K2, or you could call it Kcat, the catalytic rate, that doesn't matter, divided by Km. And the larger that number is, that means that there's less of a distinction between these two things here. That means that it's balanced, and the more balanced an enzyme is, the more balanced the K2 over Km is, the more likely you're going to have an efficient enzyme, because there's not a whole lot of deviation between those two. The last thing that I'm going to mention, and I swear this is the last thing I'm going to talk about with the concept of this, I'm going to go ahead and just write it out in purple, I know, and it applies to this as well, is that when you have a substrate concentration that is significantly less than that of the Km, when this happens, okay, your rate is going to be less than Kcat. Your rate is going to be less than that of K2, right? Because we're not even at Km yet. We're totally dependent upon, what is rate totally dependent upon? Well, it's dependent upon the substrate concentration, but also that of Kcat over Km, the overall catalytic efficiency, and then the concentration that we have here. So the way that we represent this, you can think of it as rate. Velocity is used the same way. We just simply take Kcat over Km, or I could say K2 over Km, the overall enzyme efficiency, and what am I going to do? I'm going to multiply that by whatever my substrate concentration is, all right? Up until I reach this Km point. Once we reach Km, we're not really so much worried about, it kind of you know, it's as much as I like to think of this as the rate limiting step being the delivery here and the rate limiting step being the catalysis, it's kind of a balancing act. It's not an all or nothing phenomenon. So as we get closer to Vmax, substrate concentration kind of has less of a role to do with it, and then by the time you reach Vmax, substrate concentration has nothing to do with it. So hopefully this kind of provides some substance to what we talked about and some background to what we're talking about. This is really just, for the next couple of videos, I'm only going to be focusing on the equations themselves.